Do you think that's true, Kelly? If you're out there in Cyberland, they're dissing you, said you won't watch it. We'll see if you do. Yeah, tell me the secret word. It will be Jack, Jack and Michael. Or the secret words. Whatever. So this equals this. Now it's what is like right off the bat we know we have some formulas for F friction, right? What's the formula for the friction force? Mu times F perpendicular, right? What's the formula for FC? M times AC, right? I don't know yet. It says they don't give us mass, but does that matter? Right? Not you again. It says the mu value and the radius of the road. So we can get AC from this because mu is 0.8, right? F parallel, F perpendicular, I mean, is m times g cosine theta. Oh, no, wait. There is no cosine because it's just mg mac. Now, do you remember when we said that how fast can you walk? What's the maximum you could walk? What's the maximum acceleration you can get from walking on a surface? Mu times g, wasn't it? Remember that? This is the same concept of the acceleration that's caused by the friction that's keeping the car going around the track. Mu times g. So AC is 0.8 times 10 meters per second squared, or AC is 8 meters per second squared, right? They do tests like this on them. Yeah, they test it like this. They test it with oil on the road and wet roads. Now, what's the formula for AC? So if we know AC and we know R, so V squared, whoops, V squared equals 8 times 50, or 400 meters squared per second squared. So V would be 20 meters per second, right? What do you mean, what is it? That's the velocity of the car going, the maximum amount the car should go around that curve. Any faster, it's in danger of speeding out, spinning out, and going off. We'll say 25 just for fun. I just wanted you to find V. Here's 2. Are you working with others? One of these you left, I think, here. Okay, thanks. See you. Maybe next, but we're going to try Little Timmy on page 12. Well, if I would have changed it, I probably would have. Little Tommy, 45 kilograms, is riding on a merry-go-round. The little throw is 1 diameter. So he's just standing on there. Okay. One of his feet is already gone from the last merry-go-round he was on. I noticed. So he has a mass of 45 kilograms. And as this rotates around, right, it has a diameter of 10 meters. Oh, a diameter of 10 meters? Oh, so. And rotates every 8 seconds. All the handles are broken off, so there's nothing to hang on to. It's just how much friction is going to keep them on, isn't it? Big T is a specific time to go around once, the period, to go around one cycle. He's standing on the outer rim. What's the minimum coefficient to keep him from falling off the ride? So he's going to have F, G down, and F perpendicular up. And the net force is only going to be as a result of friction. Only for that. And that FF, that frictional force, is just like the last problem, is the same. It's also FC, the centripetal force. The centripetal force always comes from combinations of other forces. The net force that's involved. In this case, it's only friction, but it could be multiple things. If it was friction and he was holding onto a bar, then it would be tension and friction that would come to produce it. So we want to find what mu is. Now, we know that mu F perpendicular equals m times AC. Let's see if we can't get AC, because we know V is 2 pi r over T, don't we? Right? And R would be what? 5 meters. And T, you're given, it's 8 seconds. So 2 times pi times 5 divided by 8, or 3.93 meters per second. That makes sense? Yeah. It doesn't matter. One of you probably knows like pi to the 300th. Memorized? I know 3. Okay, so AC, go ahead. That's 3. Then the centripetal acceleration is v squared over r, which is 5 meters again. Oh, the packets are due on Monday. If you turn them in Friday, you can get the early points for it. Extra points. Well, you get a point per page. If a point per page, you get everything right on, and you get yeah, I forget what else I give you. You don't want to turn it in incomplete, but if you have it done, it makes sense to turn it in. You don't want to say, oh, I got it early, and then give it to me incomplete without the internet questions done or something. That doesn't make any sense. No, they don't. They just take you time, but you do them. Some people don't do them. They lose like 5 points on them. All right, so we have AC. We don't even need his mass, but we have it. So mu is what we're looking for. And mu will be m times AC over F perpendicular. If I solve that for it, right? So the mass actually is not even needed. No, I got it from here. All right, come on. Try to stay with me. Okay? The sum of the force is just friction. Friction, then, therefore, is the centripetal force. Because the centripetal force is the sum of the forces. So friction is mu F perpendicular, which equals m times AC. Then we went through a process to come up with AC, and we found AC. It's this. Then if I rearrange this equation up here, I can see that mu is m times AC over F perpendicular. We don't even need his mass. And we'll have 3.09 meters per second squared over 10 meters per second squared, or approximately 0.31. Yeah, you could write that down. You should have had it written down before from earlier units. Oh no, maybe it was from the start of 5. It was from the start of 5. It's just been so long. We've been on topic 5 for 30 months. No, that is friction. That's maximum that you would need. Yes. Yes. What's the other questions? Well, I just answered one of yours. I answered somebody. What? Right below it? Sure. Is that what you wanted to? Okay. Oh, well. The military wants to put up a satellite that will orbit the Earth once every 6 hours. At what radius should it be placed? All right, so this is 5.55 on page 12 of 18. Now, what's my formula for this? In the video, I worked it out. So it orbits the Earth every 6 hours, right? So its period is 6 hours, right? And what radius should it be placed? If you found the force from F equals G M1 M2 over R squared, and AC is V squared over R, let Let me see, because I have one written down, but I don't know what I gave you. V G. Is it this V? Now here we're given big T, right? And big T is 6 hours. And well, because V is 2 pi r over T, T is 2 pi r over V, right? Oops, I should solve that. No, I should just plug it in here. Sorry, forget that. What is 6 hours in seconds? 21,600 seconds. So V, though, is 2 pi r over T. So we could plug that in. V is 2 pi r over T. I just plugged it in. That's it. Now I know what T is. Do I know R? No, that's what I want. Do I know what G, the mass of the planet, is? I can get it, though, because it's Earth. It's on your reference tables, I think. 6 times 10 to the 24th kilograms. Let's do something, though, because we want to solve for R, right? So before we go and start plugging a bunch of stuff in, we have 2 R's, so that's posing us a sort of a problem here. But if we squared both sides, we can get rid of the square root. So if we square both sides, we get 2 squared pi squared r squared over t squared. See that? I square everything. Equals g, the square root goes away. Now I can bring this r up, and I'll have r cubed, and I'll bring the t squared over, and I'll bring these down below, 4 pi squared. Now I have a formula for r cubed. So now I can plug into that, huh? So I noticed that there were 2 r's, and I was like, I got to get those together so that we could solve this problem. I didn't add them. I squared both sides. I brought it up. What's r squared times r? Cross multiply. R squared times r is add the exponents, r cubed, right? And then bring the t squared up, right? Cross multiply, and then bring this down, 4 pi squared. Make sense? So now I have a formula for r, so that will give me the radius of an orbit based on the mass of the planet and whatever period the satellite's going in. Okay? So that might be an important formula to have. So r cubed equals big G times the mass of the planet times the period squared, which was how many seconds? The mass of the planet. What? It's squared. So G times M times T squared over 4 pi squared. Calculate what that is. Try the calculation so you know how to use your calculator. 1.867 times 10 to the 23rd over 4 pi squared. You can see how these get big. It's just because it's big numbers and stuff. What? 4.73 times 10 to the 21 meters cubed. And then you take the cube root of it. 16,000,000 1.679 times 10 to the 8 meters. Why did I get 7? 3? Oh, it is 7. Wait, let me answer one question at a time. What is what? Oh, yeah, it's meters cubed. Did you square that? Why don't you have your calculator out? Yes. Oh, you don't have it. Oh, you did 216,000. Let's see. You had an extra 0. Okay, now you get it when you do that. Yeah, I wrote 8, but it's supposed to be 7. So I fixed it, crossed it out, and wrote 7. Let me get everybody on the right page here first. So that's a good formula to know, unless you want to go with what you already have and can find that on a test. If not, you should write that formula down. R cubed equals G times MP times T squared over 4 pi squared. Why? Now you, wait, what? All right, now you got to take the cubed root of that. Wait, I didn't do it yet, though. So when you have 1.867 e to the 23, right? Divided by, oh, you squared the 4. The 4 is not squared. It's 4. I already squared the 4. It was 2 squared. So it's 4, well, 4 times pi squared. Like that. Then that gives you that. And then you take the cube root of it. You could go answer, then you can go to math. Actually, don't put answer in yet. Do math, go to math, number 4, and then put in the answer, and you get it out. See? So math 4 is cubed root on yours. Uh, well, you could, the cubed root, it's raised to the 1/3, so you could always do you could do 4.73 times 10 to the 21 hat, parentheses 1 divided by 3. That's the same thing as a cubed root. What's up? It ends up being cubed because, oh, we start from this equation, right? So when we plug in t is 2 pi r. No. What the heck? How'd you get to this? Wait, look up here. This is the original formula. This is going to divide it by 4, then multiply it. You would have to say 1.86. You'd say 1.867 e to the 23rd, right? Divided by parentheses 4 times pi is it cubed? Oh yeah. Then that gives you that, and then you cube root it. What equation did you have for the period? Four pi squared. Oh, oh. I can't hear her. Stop it. What? All right, so I have to check to see if it's right. So from here, 4 pi squared r cubed. Yes, that looks right. So, all right. No, it's cubed. What are you asking me? Well, you said 4. No, wait a minute. So from this, what are you saying? You had problems from this? Oh, so now you fixed it. All right, thank you. Does it say r squared in the video notes? What do you mean, what is the answer? We wrote it down already. I don't even know what that means. Well, no, what happened was this. This is the formula I use to solve for this. They all come from the basic same place, okay? Another formula is this one. She had it written down wrong. She had it written down with r squared. But you could start from this and get to the right answer, or you could start from that to get from the right answer, okay? It's just rearranging the same thing, though. The key is that you want, I would probably put on your reference tables this equation for the period, right? And then it wouldn't be a bad idea to have like maybe this equation too. Okay. Someone started with that one. Was it Michael? So that's why we went from this. Or did I start with it? Maybe I did. No, I didn't. Someone had that equation, so we started from that one. But you could start in different places. They all come from the same place. Okay. Other problems? Wait, say that again? 70 kilogram around earmuffs. The planet has a radius. Its weight is 400 on this planet. What's the mass of the planet? Okay, so this is number 10 on 10. And it says you're going to use your formula. Fg is big G, m1 times m2. Oh, with those geosynchronous orbits and stuff, we're assuming the orbit is, the velocity is constant going around it. But in fact, if the more eccentric the orbit gets, the less that's true. So with like a comet, it speeds up as it comes in close to the sun, and then it slows down out here and speeds back up. So, but the average overall, you could still use those constant velocity and 2 pi r over t for the average radius and stuffing it close. That comes from Mr. Hiller. Yes. Some of these are watered down. He has some that are excessively violent. I had to make a little less so. Okay. Let's do this problem. We only got like a minute left. So we have that F. What are we given here? 70 kilograms. Well, that would go in one of these, right? We know what G is. Let's plug that in. We know what the mass of the astronaut is. We can put that in. We're looking for the mass of the planet, so we don't know what like M2 is. That's what we're looking for. It says that the radius is 7 million meters, so that would be 7 times 10 to the 6 meters, and that's squared for the radius. And Fg would be the force between, so that would be over here, the 400 newtons. We multiply that up first. I'll go in steps here because I did the last one too quick. 400 times 7e6 squared gives 1.96 to the 16 newtons times meters squared equals 6.67 times 10 to the minus 11 newtons times meters squared over kilograms squared times 70 kilograms times the mass 2 that we're looking for. If we divide this one by that one by 6.67, we get 2.93 or 94 times 10 to the 26 kilograms squared equals 70 kilograms times M2. Then if we divide that by 70, we get 4.20 kilograms. Oh, wait, sorry. Times 10 to the 24 kilograms equals M2. And you have your mass of your planet.